Welcome, and we're going to look at the geometry related to the dot product. But before we do this, I will give you the passcode to the final video quiz that you have to do. Okay, so the passcode is in all capital letters, final. Okay, again, the passcode for the video quiz is in all capitals, final. Okay, so there we go. Let's talk about the geometry related to the dot product. And so here's a theorem. Okay, when we use the language of theorem in mathematics, that means something that we can prove. And so we are going to prove it. But this is saying that if we have an angle between two vectors, then we can say cosine of that angle is the same as the dot product over the product of their magnitudes. So let's see how this all plays out. Okay, the proof is going to use a favorite law of ours. So let's take a look. Okay, so let's kind of just draw this out. So we know that we have two vectors. I'm going to call this vector, let's see, I'm going to do this as vector B, and I'm going to do this as vector A. Okay, and then we know that theta is the angle between them. Okay, that's all we know. Okay, but here's the thing. With our previous knowledge of vectors, we can identify that the vector that extends from here, or extends between A to B, is A minus B. And we should point this way. Okay, so there we go. Now we have a triangle. We know with this triangle, we know a side, and we know a side, we know an angle, we know a side. Wonder which one we should figure out. Or actually, in this case, we would know all the sides. Okay, so in this case, we can say, okay, I know all the sides. I can use the law of cosines. Okay, and so that, just as a reminder, this would be something like we would have c squared. Technically, it's the length of this vector c, I need to define it, is equal to the length of vector A squared plus the length of vector B squared plus 2 times, minus 2 vector A, vector B, cosine of the included angle. Okay, and so I'm using c as the same thing as a plus b, or a minus b. Okay, so let's see how this all plays out. Alright, so I know this is going to be the length of a minus b, all squared is equal to length of a, all squared, plus length of b, all squared, minus 2a b, cosine of theta. Okay, and now I have to remember that this whole thing, right, is the same as a minus b dotted with itself. So a dot product with itself. Okay, and I'm not going to write out the right side for time purposes. If I now use additional properties of the dot product, such as distributivity, I end up with length of a squared minus 2a dot b, and then plus length of b squared. Okay, and that's still equal to that. And when I go through, length of a is going to cancel, length of b is going to cancel, the minus 2a, the minus 2 is going to cancel after I do division. So really what I end up with at the very, very end is that I get a dot b is the same as length of a, length of b, cosine of theta. Oh, look. And then certainly you can divide this over and boom, you're done. Okay, I'm not going to do that last step. And in fact, many times people like using this last step to just compute the dot products. Okay, so that's another handy form of the same idea. But yay, we proved that theorem using law of cosines. Not too bad. Okay, so we want to use this to find the angle between these two vectors. Okay, so I want you to pause video, try it out for yourself, try using this formula, and then resume when you're ready. And so here I did the dot product, minus 13, got the length of V was square root of 17, length of W is 29, square root of 29, and then I just used the formula, or you could use this form as well. And at the end of the day, after I rounded and did inverse cosine, I got 125.8 degrees. Okay, great. So moving on with our life. The other thing that you really should do is just kind of maybe verify this with a little sketch. So if you do, these are in standard position, right, you'd have 4 minus 1, so you'd have something like that for V. And so this is V, and then W is minus 2, 5. Right, so you're up here, something like that, W. And so does your answer match reality? Yeah, it seems so here. It is plausible that that could be 125 degrees. Okay. Now, as a way to think about some properties related to the geometry here, the question I have is, what is the dot product if two vectors are parallel, or what if they are orthogonal? And another word that we use for orthogonal is perpendicular. So from our past experience, we might know that if we think about two vectors, or two lines really, that are perpendicular, the angle between them is either 0 or pi, so it could either be, if they're pointing in the same direction, it would be 0. If it's pointing in the opposite, if they're pointing in opposite directions, it would be pi. So then what do we get here? So we'd have, remember the definition is cosine theta is equal to, A dot B over length of A, length of B. And so if you evaluate cosine at 0 or pi, right, this ends up being either 1 or minus 1. So in the case of parallel, we either get that A dot B, if we think of this as plus or minus 1, this could be either plus or minus the magnitude of A times the magnitude of B. Okay? In the case that they are orthogonal or perpendicular, right, that is where the angle between them would be 90 degrees, pi over 2. So then in our definition, cosine theta is equal to A dot B over length of A, length of B. Oops. This would be 0 is equal to A dot B over length of A, length of B. And so really 0 would be the same thing as the dot product. So the benefit, or the upshot of all this, is if we ever get a dot product that is 0, that means that the angle between them is pi over 2 or 90 degrees. Okay, so that is some very useful results of the geometry here. Okay. Other than that, remember these key properties as well as the definition that we get based on geometry for the dot product, and you'll be good to go.